Do you see now the different slides?
Yes, we can see now.
Okay, perfect. I think you saw then only the beginning side, isn't it?
Yes, first we have only seen the first slide. Now we can see long versus distributed circuits slide.
Okay. Then I will shortly repeat it. So here on the right side, you see is a lumped circuits. So it's inductors, this one inductors, resistors, and capacitance. And we have also the distributed circuit. This is here, example, only a line. And in this example, I showed that, for example, for 300 megahertz signal, so it means lambda is equal to 1 meter, and 25 centimeter line, we have at each point a different current. And this is, as you see, only important if you have high frequency signals. So it means a digital signal or an analog signal, what I compared here. So on the left side, we see the digital domain, so a digital signal with a rise time and fall time. And on the right side, we see a normal analog signal, very bad drawn analog signal. So if you do a design, you have to decide what kind of circuit you are using, the lumped or distributed circuit. So in the digital domain, the signal path can be treated as lumped element if the rise time divided by the time delay is greater than 6. Then you can only use lumped elements for your simulation. And if the rise time divided by the time delay is smaller, should be smaller than 2.5. Smaller than 2.5. Then you have to calculate with distributed elements, because at this point the phase are very important. But this distributed element is very complicated to understand. Therefore, if you need more information, then you have to read the microwave engineering book. This is from David M. Potzer. This is a book about microwave and high frequency design. And there you have learned a lot about S parameters and the waveguides and so on. And also for the analog domain, you can use lumped element if the distance between the beginning and the end is smaller than 0.1 lambda, or better if the distance is smaller than 0.01 lambda. At this point, you can neglect then the matching. But also in this area, we're using transition lines for match some signals, for example, for USB. But next week, we will talk a little bit more about this. So now we come to the voltage divider. You know it already that the voltage divider is only two impedance and one output voltage here. And the output voltage can be calculated with C2, so this impedance, divided by C1 plus C2 times the input voltage, if we have here ground. Or also in transfer function, C2 divided by C1 plus C2. And if, for example, you put here resistance and here a capacitance, then it's a normal low pass filter. And if you have your two resistance, then it's of course only a voltage divider. So for example, do a little bit of calculation. If R1 is 10 kilo ohm and R2 is 20 kilo ohm, so only resistance, and Vin is 1 volt, and we have no output load here, so that means no output currents. We can calculate the output voltage, and this is in this case 0.66 volts. So I give you also 3 different examples for voltage divider. And first of all, you have to check the small and the large signal. So large means the DC signal, and the small signal is the AC signal. Here, the DC signal is going through the resistance to the output and also the AC signal. But the bad thing here is that you divide not only the DC and not only the AC, you also divide your own the DC signal. For example, if DC is 1 volt and AC is 1 volt, we have here 0.66 volt DC and 0.66 peak-to-peak AC signal. So this can destroy your circuit, or not your circuit, so it can destroy your condition of your op-amp. So your stable condition. Therefore, it exists also a voltage divider with capacitor. So you have only the AC true from input to output. So the divide, for example, if you have here 1 volt, then you have here 0.5 or 0.66 volt, depends on the size of the capacitance. But this is a DC blocking. So you have no DC voltage at the output. So it means if you have your op-amp here, the operating point is destroyed. Therefore, you can put an easy resistance here to feed the output with the DC here. So here you have an AC voltage divider with only C1 and C2 if R1 is very high, and you have the DC feed here. But the DC is not divided, so only the AC is divided. But later on we are using only this one for future calculations, because a conductor or a line is more resistant in low frequency. So now we come to get conductors. This is more interesting thing for you. So a conductor have a length, so the trace length, and a width, and also a height. And all wires or conductors on PCBs are resistors, as well as inductors and capacitance. And for high precision systems, this resistance here, the trace resistance, can reduce the system performance. And we'll do also some example later. And you can calculate the resistance with R is equal to rho, so this is the resistivity of the copper, because normally the traces are copper, times the length divided by 5 times T. And T is the height of the copper, so it means, so often it's given from the manufacturers in ounces. So 1 ounce is equal to 0.0347 millimeters. So a small example, for if you said, okay, your line is 50 millimeter long, you have a 1 ounce copper, and your width is 0.25 millimeters, then first of all, if you have 1 ounce, your T is 0.0347 millimeters, and then your resistance is equal to 0.1 ohm. So R is equal, don't know why it's changed here. So R is equal to 0.1 ohm. So now let's do a system example for a precision measurement. If you have a signal source, what gives 1 volt peak-to-peak signal, you have here a trace, so the same trace as we calculated before, and we have here 60-bit ADC with an input resistance of about 5 kilo ohm. And let's assume we have an ideal ground path. About the ground, we will talk this about, I think, in 2 or 3 weeks about the ground problem. Now you can first calculate your resolution of your ADC. It means 1 LSB is equal to 1 volt, so maximum volt, divided by 2 to the power of 16 minus 1. So that means we have a resolution about 50 microvolts here. So the minimum voltage what we can measure is 50 microvolts. So now we have to calculate the voltage drop about the trace. This is easy. We have here a voltage loop. That means 1 volt here minus the voltage divider here. Then we have the trace, the voltage drop over the trace. So again, here is R in 5 kilo ohm divided by R trace 0.1 ohm plus 5 kilo ohm times the voltage, the input voltage, and then we have about 20 microvolts. So you see we have a higher voltage drop compared to our resolution. So we lost over 1 LSB. And for precision measurement, this is a lot. Okay, in this example, we lost 2 LSB. And this is also called gain error. I can show you in the next slide the transfer function. But you have to keep in mind, we ignored here the trace inductance and the ground noise and also the temperature change, because this should thing also decrease the performance of the system.
And this is a short reminder for
ADC transfer function. So ideal, the transfer function is here. So you have here normally a step. And if you lose LSB, for example, here minus 1.5 LSB, then you have a gain error. You can see we never reached this point and also this point. So we lost this to LSB. And this means also that your measurement is not exact and not precision. But this is only important if you really do a precision measurement, for example, with 60 or 2040 bit ADC.
there exists a lot of
Solutions to decrease some problem of the traces. For example, the Kelvin circuit. That means you are using more wires for cancel out the voltage drop. But if you have more signal sources, then you have, of course, more traces and make the circuit bigger. Therefore, it's important to do the trace, so to design the trace such that you have a very low impedance or a very low resistance. If you go back to decrease the resistance here, you have to decrease the length, or you have to increase the width or the copper thickness. Both is possible. But the better way is to decrease the length. Now let's talk about inductance of conductors. This is more complicated formula. So the PCB traces are not only resistors, as they are as well inductors. And this is a problem for high frequency systems, or if you have clocks on your trace. And with the inductor, you can calculate this formula. This is very approximation of this inductance. So this is not 100% exact. You can say that it's error about 20%, plus minus 20%. And if you use the same sizes as before, then we have a 63 nanohenry inductance of the trace. So for example, if you have a 10 megahertz signal, resistance is then 4 ohms. So it's much higher than the 0.1 ohm. So it means if your signal source has an input, what your signal source see is only an inductor. And this can be a problem for high frequency. So you have then a mismatch and you will lose energy. Or your clock will not look like this, so it ends looks like this. This is then very bad for your future systems. It can also be possible that you can never reach the 100%. If your inductance is very high. Therefore, we are doing a lot of matching with clock signals. For example, USB, I2C or SPI and so on. But we will talk about it next week. And of course, if you have the round plane on the bottom, you have also a capacitance between this trace and the bottom plate. This is equal to the epsilon times the area divided by the distance. So the area is L times V, so the bottom area. And of course, if you have two lines parallel like this, then you have also a capacitance between these two lines. And this is the crosstalk. So here, A is then L times T. And let's say if L1 is a normal clock signal, and you assume that L2 is a normal DC signal, then at the end, what you see at this point is a signal like this. So you have a distributed signal. And this noise or this crosstalk can also decrease your system performance. So it means that if you have a clock line and if you have a second line for the DC line, you have to increase the distance here to avoid crosstalk. But about crosstalk and electromagnetic interference, we will talk about it in 2 weeks. Yeah. So, about temperature. So temperature is very important because you can see here in this formula, let's say this is the temperature change, delta T. If the temperature increase of your trace, then the resistance increase. And here alpha is then the temperature coefficient of kappa. And if we say, for example, okay, we have a 10-degree decreasing of the temperature, then we have about 4% more resistance. And if you increase a lot of the temperature, then you also increase the resistance. And the thermal can have a flux. So that means the thermal flows from one point to the other point, and you can also heat other components. 2 years ago, I designed a DC-DC converter where I didn't check the thermal formula here. And at the end, my traces heats up. The traces heats then also my inductor hot up. And then at the end, I had no DC to DC converter. I had a DC to small converter. So my inductor was smoking. This is very interesting, but not too good for your DC-DC converter. So take care about the temperature. And of course, you can also calculate then your current. So you have to decide what are my 5 and what are my high of the traces to reach some currents. And this formula is a very rough estimation. So that means that's the maximum current what you can reach with such a conductor. And these values are taken from IPC 2221. So this is an industrial standard for current calculation of a conductor. And here you see also the temperature is very important, the temperature increasing. So this example, let's say we have again 50 millimeter length. We have 1 ounce copper. We have 0.25 millimeter wide. And we have a temperature increasing of 20 Kelvin. With such values, we can only have 1.13 ampere through this wire. If we put more ampere through this wire, then of course the temperature will increase because T and V are technology parameters or design parameters, and delta T are the environment parameter. So if you design then a power system, for example, if you want 100 ampere, then you have to increase the T. So that means the copper material, or the weight of the copper material, or you have to increase the width. But if you increase the width a lot, then you can have 100 millimeter width, and this is also a lot. And you know, if you have a wide width, you decrease your resistance. So, but if you increase your T, then you have to keep in mind that you need a minimum space between these two lines. This has an easy yes, this is because of etching. So here's an example how to etch or how the PCB are etched. So we have here resistors. We have here full copper and here laminate. And after etching, you see that we have here some decreasing. So the size here on the top is lower than the size on the bottom. And this is the reason why you need a minimum distance of the copper if you increase the T. So if you increase the T, then its end can look like this. And the width, what you design, is here in the middle.
Thickness increase गरेर भने त्यो कपरको त्यो ठुलो हुन्छ भनेर
Therefore, take care about the distance, and also the crosstalk happens exactly here. This is also very important for the crosstalk design. So to decrease the crosstalk. So now we go to the wire. There exist 3 types of wires. So one is the true wire. This is a common use wire. Then the second one is the blind wire, and the third one is the buried wire. So blind wire means that from top or bottom layer to the middle layer, and the buried wire is inside the PCB. So if you have a 4-layer PCB, these 2 wires are very expensive, therefore they are not often used. The common use wire is this one, the true wire, because this is very easy to manufacture. And it also exists thermal wires. Here on the right side, you see one thermal pad of IC, and a lot of thermal wires. This is 64 thermal wires. And these wires are used for dissipate some energy, the thermal energy, from the top layer to the bottom layer. And the right choice of the wires, you can read it in the datasheet of the IC. So the IC datasheet gives you the amount of wires and give you some explanation how to use it. And also power MOSFETs need thermal wires, because the power MOSFETs can increase the temperature to 100 degrees. So you have to cool down your MOSFETs, because high temperature means also higher resistance, and that means also that you decrease your system performance. And this is a model of a wire. This is the hole here. Let's say we have top and bottom layer. Here's a hole. And the inductance is exactly here, from the top layer to the bottom layer. And of course, you have also capacitance here and here. So for low frequency or the DC design, this is not important. For you, it's important to check it, from the manufacturer, what is the minimum size what you can use. And for your design, you use then the minimum size of the wire. Of course, if you have large currents, then you need also a big pad for the wire. And for high frequency signal, you have to avoid such wires because of this inductor here. And this one creates also a resonant circuit. That means if you are high frequency here and you are into the resonant, then your circuit is oscillating. This, of course, can also destroy then your system performance. And this is a rough estimation of the inductance, how to calculate it. And H is here the height. So that means the distance between here and here. And D is the diameter of the hole. So let's talk a little bit about positioning or board layout. First of all, you have to check what kind of components do you have. What are the analog part, what are the digital part? And then you have also say, okay, here on the left side, I have only the analog part, and the right side, I have only the digital part. And these 2 parts need 2 power supplies and also needs 2 different grounds. The reason is that the digital signals have a lot of noise on the ground, and you don't want this noise into your analog signal, because noise in analog signal means that your precision goes down, or you decrease your precision. Therefore, you have separated these 2 parts. And the important thing is that your ADC has 2 different grounds. Has an analog ground and has also digital ground. But the digital ground are not connected to this digital ground. This digital ground means only that in the internal ground of this ADC is connected to the digital part. But this digital ground you have to connect to the analog ground here. Also the same reason, because you don't want the digital noise into your ADC. Therefore, you're connecting both grounds to the analog ground. This is an example of a board layout. So you say, for example, here on the top left side, you have only the power supply, the DC converter, and so on. On the right side, you said, okay, I have only my digital part, and the bottom side, my analog part. And it's also very important that the high frequency parts here has the biggest distance. The reason is also because crosstalk. You don't want that this high frequency part goes to the digital part, or this digital high frequency part goes to the analog part. Therefore, the high frequency part needs the biggest distance to avoid crosstalk.
And of course, you need some
grounding and so on, but about grounding we will discuss it later in 2 or 3 weeks. And I will give you 2 advices. Always do back annotation and prototype all analog circuit, because analog circuits here are the most difficult circuits to build, because you have noises, you have mismatch, you have some performance decreasing due to resistance, inductance, and so on. And back annotation means that you're doing a schematic, then you're doing a layout, and then from the layout you know the few wires, so you have to calculate per hand or with a tool the resistance, inductance, and capacitance of the traces, and put these values back into your schematic and simulate it again, because then you can see some problems. And after that, you start a prototype. And of course, in prototype, you can see more problems, then you have to figure out what are the problems and where it comes from. Yes, and a good white paper about op-amps and how to design a schematic on the layout is from Texas Instruments, and it's called Op-amps for Everyone. So this is a very good white paper about this theory, about op-amp theory, and also about board layout for op-amps. Yes, this was my presentation. I was too fast. Do you have any questions? What I showed you is the very basics about traces, but the basics are very important for your design, because the basics makes the most problems. And next week we will talk a little bit about clocking and how to avoid some clock problems with mismatch and layout design and so on.
What is the error in PCB board in 1 ounce copper?
What is the question exactly?
What is the percentage of error in thickness of a copper board that we
So I hear only an echo. Maybe you have 2 microphones on.
Sorry. Ounce of copper bro. Here.
It's copper size you 1 ounce. This is the standard what all manufacturers gives you, and this is also the cheapest
1
one.
ounce.
If you are using 2, 3, or 4 ounce, then this increases a little bit this price. But you can see, for example, here, if you increase the ounce size,
in 1 ounce.
you can
How much of thickness either?
take more currents through the wire. This is one important thing. And also, if you go here, if you increase the ounce here, you decrease the resistance of your line.
What are you saying?
How much thickness of your within 1 ounce copper board?
There was a question in chat. The question is how much thickness of error do we get in 1 ounce of copper board? Yes, you can say. You think you mean the thickness error? It can be about 10%. But this depends on your manufacturer. So if you go to the manufacturer what can do precision PCB boards, then the error is small. Or if you give a higher price, of course you can decrease your error. But normally you have about 10% thickness error.
Thickness errors, it depends on the manufacturer.
अनि के राख्ने भने त्यो कपरको त्यो
And for low frequency or DC design, this is not so important. Also for the currents, this can be a problem if you have a high frequency design.
Like, do you say that we get the percentage of
And
error
also
depends
your wire,
on the
if you have a
manufacturer?
cross section. The wire is not normally flat, so normally a wire is like this one, so the surface. And this can also be a problem for RF design. So for RF design, high frequency design can be important. So in gigahertz area, it's very important that you have a very exact trace. But normally you will not have such high frequency on your board because such high frequency or analog circuits are integrated circuits. You have only lines if you have an IC, let's say 5 gigahertz IC for satellite communication, then you have only an output, an antenna. Therefore, only this trace is important for you, and then you have a digital output. This is a normal case, what you will have. And for this antenna, you need a magic network. But then you have to read the datasheet of the circuit here, of the IC, and the datasheet says you how to design the traces, how to design it for the optimal case. So therefore, it's always very important to read the datasheets of your integrated circuits, because they are giving you a lot of advices how to design.
Okay. Thank you, Manu.
One is something what you have to keep in mind, because for example, the keycard doesn't know that the currents through the wire increase the temperature. This is something what you have to calculate per hand or simulate with a higher performance tool. For example, Altium. Altium can also simulate the temperature on the wire.
We got our answers.
Yes, so we got our answers. And do we have to look the data sheets about the ICs?
Yes, it can very
Be helpful to do it because a lot of data sheets gives also hints about trace design or ground design or supply design. And they're always all saying, okay, if you have here an amplifier, AC, what is the size of the capacitor for the supply? It's also given in the data sheets. And also whether you only need an SMD or also an electrolyte capacitor and so on.
Paths for AC and DC current.
And if you buy an op amp, AC, then it can give you advice to buy one with 2 op amps inside. Because yeah, it's my rubber. Okay. If you have only one op amp inside, then you have the output on the right side and 2 inputs on the left side. It means if you have a feedback, you need long traces. If you buy an op amp or white spaces, so if you buy an op amp or if you buy an IC with 2 op amps, then you have normally op amp on the left side, op amp on the left side, here 2 inputs, and here the output. That means that you can put a feedback here, and you have very low, also low distance of the devices.
AC and DC currents.
And low distance means also that low resistance and so on. Therefore, you have to check where are the pins and so on. Yeah, questions?
One more question. Do we need to make different parts for AC and DC circuits in PCB circuit board?
What do you mean?
Do we need different paths for different paths for AC and DC currents in PCB board?
You mean the paths, for example, resistance and capacitance?
Yes.
Yes, you need different parts because some resistance in DC has, some resistance in AC has a parasitic capacitance, but you also can do a mismatch in the circuit. Therefore, you have to also take care about the materials and also what kind of parts you are using. And also there are some classes for parts, for example, for resistors that describe what are the power of the transistor, what are the heat of the resistor. But we will discuss it also in 4 weeks about the components, about the materials of the components, and also about the PCB material. Because it's also a very important thing.
Okay. Can you provide us these slides?
Yes, of course, I will provide it. Yeah.
Okay, thank you.
I think we can end this now. So it's okay. Answer the questions. And if we
I
get
think
any
we are able to know much information about PCB designing today, and so I think you can provide the slide, and we will just obviously see the slides. Yeah. So I think
It will be nice if you check the slides, and if you have some questions, write to me.
In the next week, I can answer the questions.
in
If you
next
want,
session,
of course.
in next session, are we doing some works in KiCad? In next lecture.
You can also do some simulation, for example. Like this. So you say you have a signal source, you have a trace, and you have an ADC. And you don't care about the ADC. You say, okay, I have only one trace. I lay out a trace. I know that this one has a defined input capacitance, defined resistance, and this system has defined input resistance, defined inductance, and so on. And to simulate it, what happens with the clock signal, what happens with the AC signal, and what happens with DC signal. Because the input impedance of the system is also very important for your system. So if you have a trace, you cannot ignore the input resistance or the input capacitance. Also, for example, if you have here clock generator, and here you have an ADC who needs the clocks here, and you know, okay, the capacitance is here 10 picofarad, and you have a high-speed clock. Then at the end, what you get here is not a perfect clock. What you get is clock like this. If you have a long wire here. And this one you can simulate also with keycard. So put a clock source here, a long wire, and then measure the clock here, this point.
Can you repeat where to put wires here?
It's a wire between your two system, or between your signal source and your load.
Between the signal source and ADC?
Now we can. Okay. So, here. You can put beginning a clock generator, for example, let's say 5 megahertz clock. Then you have a trace here to design, and then you have a load here, for example, resistance and a capacitance. And this load simulates your ADC. But if you want more accurate, then you have to check the datasheet, and then you will see that the most ADCs have a switch capacitor inside. That means they have a capacitor and they have a switch here, also with a clock. And this one you can simulate it in KeyCut. Then you can say, okay, I have my trace at this length and this width, and then you can simulate the resistance and capacitance of the trace, and you can see then what happens with the clock at this point here. And what kind of problems can occur. And this is something what you have to do later on in PCB design. So you have to simulate each trace, to simulate each clock on the trace, and to figure out what happens there to avoid some problems.
Okay, thank you.
Thank you. I think we will surely do this in KiCad. I think
We don't have any questions for today.
we don't have any more questions now.
Yes, if you have questions, please write me, and I will answer them directly, or I will give the answer then next week.
I think if any questions occurs, we can mail you, and we can discuss the questions in another session.
So, question, then the session is closed. I think.
Thank you, sir.
Thank you so much.
On Friday. At the same time, video on.
Then we see us next week. Bye.
Bye.
Bye bye.
We will see
See
on
you
next
then.
Friday at same time with the same link.
At some time. Exactly. Perfect.
Thank you.
Thank you.
Bye.
Bye bye.
ल भयो है विसम्मन खुसी चाहिँ बिने छ होइन त्यसो त नि नक्सनीबाट के राखेको भने काम
आवाज गर्नुपर्छ होइन?
यहाँ